In this problem, we're given a three-dimensional position function, and we're asked to answer several questions about the situation. In this problem, x and y are on the ground, and the z-axis is going to be up, off the ground. Now it says that there's going to be a stone rolling off a high rooftop. So I'm going to go ahead and draw a building that our stone can roll off of here. Our stone is located right in the corner. And if you notice here, our initial position in the z direction is 19.6. So that's actually going to be the height of the building. And that's going to be the answer to A. So plug in a time of 0 into the formula. And we get R of 0 is equal to 19.6 K. So it's 19.6 meters off the ground at the start. Next it says, at what time t does our stone hit the ground? So we want to let z equal 0 and find out at what time does that occur. Well, for that, we could just focus on the third dimension. It doesn't really matter where it's located as far as x and y go here. We just need to make sure that our 0 is equal to 19.6 minus 4.9 t squared. Okay, let our third component be 0. Then we know we're on the ground. So just go ahead and solve that. It happens at t equals 2 seconds. Now we want to write a vector which indicates where our stone hits the ground. So using our work from above, we want to let t be 2 because that's when it hits the ground. So let's find r of 2 then. Okay, I get 8i minus 8j, and plus, of course, 0k. So somewhere out here, how fast is the stone moving when it hits the ground? Okay, so for that, we're going to want to find a formula which gives the speed of our object. First of all, let's find the velocity of our object by differentiating. All right, so our velocity function here, take the derivative of the position function, which is 4ti minus 4tj plus 19.6 minus 4.9 t squared k. All right, we want to take that first derivative. And let's see, we're going to get 4i minus 4j minus 9.8 tk. All right, to figure out how fast it's moving, though, we're going to want to take the magnitude of this. So we're going to get 4 squared plus negative 4 squared plus negative 9.8t squared. Go ahead and let t equal 2 because that's the time we're interested in when it's hitting the ground. We can see right here it hits the ground at t equals 2. So let's find the speed of this particle at 2. Okay, that's going to give us 16 plus 16 plus negative 9.8 times 2 squared. .4 meters per second. Okay. All right, next we're asked to find the shortest distance between the point where the stone was launched and the point where it hits the ground. All right, so if this were just a two-dimensional problem, we would use Pythagorean theorem for this. We'd have an initial point and a final point. We'd make a triangle out of it. We want a straight line being the shortest distance between those points. But what are the coordinates of those points? Well, our initial point, according to the work that we had done earlier, is going to be 0, 0, 19.6. And our final point will be, according to the work we had done, 8, negative 8, 0. All right, in 3 dimensions, to get the shortest distance between 2 positions, we need the magnitude of delta r. Okay, so I'll use a magnitude formula. I need delta x squared plus delta y squared. And since we're working with 3 dimensions now, we also need delta z squared. Okay, so let's plug these in. We want x final minus x initial, y final minus y initial, and z final minus z initial. 8 minus 0, and we'll have negative 8 minus 0, and 0 minus 19.6. Plug that in. You get 22.6 meters as the physical distance between those points. But our projectile is not going to move in a straight line. It's going to move in a curved arc instead. And we'd really like to find what's the actual physical distance that our projectile is going to travel in going from the top to the bottom. In other words, what's the arc length of that path that it actually takes? And of course, our arc would be a curve, a parabola. So that requires calculus to find that answer. So what we want to do is we want to start off with the idea that an arc length can be found by integrating. What do we integrate? Well, we have to know, first of all, how fast we're going. Okay, so put your speed function in the integral. And we have to do the speed times dt. Okay, so this comes from the fact that a tiny change in arc length will be equal to the speed that you're traveling times a tiny change in time. All right, if you zoom in on a piece of the curve, okay, we need to go from here to here. That's going to be ds. That's going to be the arc length of that tiny little section. You have to know how fast you're going, which is the speed. And you have to multiply by the time. So if we go in and then integrate both sides of the equation, that's how we find the arc length. But we have to go from some initial time to some final time. Luckily, we already found a formula for the speed. So let's go ahead and plug that in. We're going to go from t equals 0 to t equals 2. Plug in our speed formula, which is 16 plus 16 plus 9.8 t squared dt. And now this is the kind of thing that we can actually plug into a TI-84 calculator, or we could do this in symbolab.com, for example. I'll just do this on Symbolab here real quick. All right, let's go from 0 to 2. Plug in our speed formula. And end it with a dt. It should give us a numerical approximation. Yeah, there we go, 23.6. Now, as we can see, we can verify that the actual arc length our stone travels is just a little bit longer than the shortest distance between the points that we found earlier. Does it seem reasonable? I believe it does. Alright, if you're using a TI-84, the way to evaluate an integral like this would be to use the math button. Okay, then you're going to want to do choice 9 here. And you can enter your limits. You want to plug in your formula. Alright, that looks pretty good there. Let's see if the calculator gives us the same answer that Symbolab had found. Yep, looks good.